So I want to speak about floating bodies and our extension of floating bodies into space curvature. And this recent contribution, which is now on archive, jointly with Elisabeth Werner, where we now study floating bodies in combination with duality. Okay. So to start off, let me give you a brief what we call the notion of affine surface areas, and let's start with the classical notion by Blaschke. So when we have a convex body K, and for now let's assume it's regular enough, so we have a twice differential boundary with everywhere positive curvature, then we can define affine surface area as defined by Blaschke in low dimensions for regular bodies, either by integrating the Gauss-Kronecker curvature to this power 1 over n plus 1 over the boundary. So here this is my notation for the usual surface area measure. Or you could equivalently write it using centro-affine notions, so you can integrate the centro-affine invariant curvature to this power with respect to the cone volume measure, right? So to be a bit more precise here, so with hi minus 1 here, we denote the Gauss-Kronecker curvature, and when we drop the regularity assumptions on K, we then use the so-called generalized Gauss-Kronecker curvature, which still can be defined almost everywhere on the boundary of K. And the centro-affine curvature, well, you can define it using ellipsoids that oscillate, so touch at of second order your convex body from the inside. And you can also express it with these Euclidean terms. So what you can immediately see is here we have an expression that uses Euclidean notions. So you have rigid motion invariant, you have a translation invariant, rotation invariant quantity. And when we define it using centro-affine invariant notions, it will be centro-affine invariant. So it has both these invariances, so it's invariant with respect to volume-preserving affine transformations. Okay, yeah, so for a cone volume measure, sorry, you also have this expression. So you can see it's absolutely continuous with respect to the Hausdorff measure, and the density is just given by the distance to the hyperplane, to the supporting hyperplanes. Okay, so this is a very classical and important notion, and the interesting question was, well, can we drop these curvature conditions on K? And yes, indeed, there is some natural extension of this Blaschke's affine surface area to general convex bodies. This was proven sort of independently after a long time by Leichtweis, Werner, and Lutwak, who gave different extensions at first, and then it turned out that all of these extensions give you the same expression essentially on the sets of convex bodies. And there is also a very nice characterization in terms of affine invariant valuations. So Ludwig and Reitzner, they showed that affine surface area is essentially the only upper semi-continuous equiaffine invariant valuation on convex bodies. So equiaffine invariant valuations, there are actually just 3 examples: the volume, the constant function, the Euler characteristic, and the only semi-continuous one is the Blaschke's affine surface area. Okay, and then I should also mention that there are many extensions of this notion. I will not focus on functional analogs, but there are quite a substantial body of results here. So there are some sort of functional analogs of this notion, of this construction, but this will not be the focus of this talk. Instead, I want to move into the family of LP affine surface areas. So this first generalization of Blaschke's affine surface area was maybe introduced by Lutwak, the so-called LP affine surface areas. So they are not affine invariant in the same way as the Blaschke's affine surface area, they are just centro-affine invariant notions now. Okay, so you see you can define them again as a sort of curvature measure where you take the centro-affine curvature to this power now, and they have been studied in various directions. Essentially, you can define them for all p not equal to minus n, but I prefer to write here p bigger than minus n, so that this quantity is semi-continuous, and when you want to have p less than minus n, you should define slightly different so that you have at least lower semi-continuity. Okay, so what are the properties of these functionals? Well, they are the canonically homogeneous examples for centro-affine curvature measures. And the degree of homogeneity, Q here, is controlled by P in this way. And there are special cases. So for P equals 1, you have Blaschke's affine surface area, which is not just central affine, but also translation invariant. And for P equals N, you end up with the zero homogeneous case, the classical so-called central affine surface area. And in the range where P is positive, these measures, they are upper semi-continuous, and if P is negative, then they are lower semi-continuous in general. In particular, this means that if your degree of homogeneity Q is strictly between minus n and n, you have upper semi-continuous notions, and if the degree of homogeneity is an absolute value bigger than n, you have lower semi-continuous notions. So you can sort of draw all of these quantities on the real line where you enumerate the degree of homogeneity. So in the range between minus n and n, you have the upper semi-continuous case, you have Blaschke's affine surface area appearing here. You have sort of a duality formula which moves from the degree Q case to the minus Q case by looking at the corresponding LP affine surface area of the polar body. So this polarity formula, I will say, is due to Hooke. And in this way, you have a sort of reflection formula on the degree of homogeneity using the polar body. Okay, so in the limiting cases, you have the volume, which is the continuous quantity, and here for the negative degree of homogeneity n, you have the volume of the polar body, which is also continuous. And then when you move outside the range of degree of homogeneity bounded by n, you have the lower semi-continuous case, and I have highlighted here one particular LP affine surface area which will be of importance to us with P of this degree here. Okay, and I want to mention here some characterization results for these quantities as well. So again, due to Monika Ludwig and Matthias Reitzner, when you are looking at upper semi-continuous SLN invariant valuations enumerated by the degree of homogeneity, then exactly these LP affine surface area are the only examples that show up. And this was then further further extended. So these LP affine surface area can be further extended into general affine surface areas, and they are the natural family that appears here are so-called Orlich affine surface areas, and at least in the upper semi-continuous case, they have been characterized in a way similar to Hartwig's theorem for valuations. Continuous valuations, rigid motion invariant continuous valuations. Okay, so and of course these quantities, these affine surface areas, they also appear a lot in random polytopic approximation or optimal polytopic approximation. And again, I will not go into the details here. I've listed a lot of names just to mention this. These quantities, they naturally appear here as well. Okay, so we want to look at LP affine surface areas not in Euclidean space, but in spaces of constant curvature. And our approach here is to look at floating bodies, and we can use floating bodies to introduce Blaschke's affine surface area. And combining floating bodies with polarity, we actually can, at least for one particular case, also define the LP affine surface area in a geometric way. And this is what we wanted to generalize into non-Euclidean spaces. Okay, so you have seen the definition of a floating body yesterday. I want to recall this. So what we are doing is we have a convex body K, and we are now looking at intersections with half spaces such that the volume of these caps is fixed. Okay, so for us it's convenient to write this not fixed, but as a lower bounded by delta. So essentially you have a convex body and you come off caps and you impose a bound on the volume of these caps. If the volume of the cap is less than delta, then you cut it away. And as we have seen yesterday, you can think of this as sort of a geometric construction. You think about your hyperplanes as the surface of water. And your body is sort of floating when such a volume condition is satisfied. So think about some object floating in a body of water, right? So the Archimedean principle tells you it floats when the water that is being displaced by the submerged part is equal in weight to the total weight of the body. So this can be translated into a volume ratio condition, and in this way we can think about this K to be some floating object, and when we rotate it, the red part, the floating body, will always be below the water surface. Okay, so in this way we get a geometric construction that is controlled by one parameter delta, and as delta goes to 0, it converges to our original convex body in the Hausdorff metric, and it's an affine covariant construction, so it commutes with the affine group. So, okay, so in a sense, you have a family of inner parallel bodies, and as you have seen in the morning by Galina, when you have, so she was defining the perimeter of a set by looking at the volume derivative, or measure derivative, Gaussian derivative, Gaussian volume derivative, when you have an outer parallel body. And now using this inner parallel body, we do the same. We want to have a volume derivative of the volume of the floating body, and this gives rise to a curvature measure, and it turns out that this is exactly what can be used to define Blaschke's affine surface area for general convex bodies. Okay, so this was the approach by Schütt and Werner, generalizing results by Blaschke and Leichtweiss. For any convex body, you can show that this volume derivative exists in this form and gives rise exactly up to the constant to Blaschke's affine surface area. And as I said, we want to use the floating body and polarity to define curvature measures. So the polar body, when you sort of conjugate our floating body operator with polarity, so we take the polar body, then we apply the floating body operator, and then we take polarity again. Then this gives you another natural way to associate to K an outer parallel body now. And because of the polar body is a centro affine contravariant notion, and you do it twice, so it becomes centro affine covariant. And the floating body, as we said, was affine invariant, so actually this construction gives you a centro affine way to associate an outer parallel body to K. And when you take the volume of this object, it gives you a centro affine invariant curvature measure, and this has to be, in a sense, it's natural that this is an LP affine surface area, and this is verified by first Meyer and Werner, and then in another way by Werner and Ye, that this is true. So when you take the volume derivative of this polarized floating body, you get exactly an LP affine surface area of this form. Okay. So we have to restrict ourselves here now again to the positively curved case, because otherwise these quantities become unbounded possibly. So if you have a C2 plus convex body, then these will be finite on the right hand side. Okay. Now, the next step for us was to generalize floating bodies to weighted floating bodies. And the idea here is to use weighted floating bodies to replace the Euclidean structure of the space with some non-Euclidean structure. Okay, so what are weighted floating bodies? Well, you can just take some continuous weight function and replace the back measure, volume measure with these weighted volumes. And in this way, you, in the same way as before, you can just cut off now caps with weighted volume delta, and you obtain again some convex body inside that converges in Hausdorff metric. And some equivalent way to think about floating bodies is using density functions or depth functions. So this is maybe more related to the idea of Baroni and Lahmann, how they approached floating bodies in their work. So we can think about the floating body as the natural superlevel set of a depth function, of a half-space depth function, and this also works for the weighted setup when you replace these volume depth functions with weighted volume depth functions. Okay, so some basic properties, obvious properties. You have monotonicity on the level of sets and on the level of weight functions, and you have convergence in the Hausdorff metric as delta goes to 0. So all of this works nicely. You have some, in the smooth case, you have some explicit bounds on the Hausdorff metric, and you can actually write a derivative almost everywhere. Okay, so the weighted volume of weighted floating bodies was studied in joint work with Monica Lutwak and Elisabeth first, and it gives rise to some weighted notion of affine surface area. And now in the more recent work with Elisabeth, we are now looking at the weighted floating body conjugated by polarity. And again, we can show that this gives rise to a weighted notion of this LP affine surface area, where the weight functions enter in terms of the boundary points of K and the boundary points of the polar body via the polar point map. So if you have a smooth convex body, every boundary point of K can be uniquely associated with boundary point of the polar body. And this is what you use here. Okay, so we find that this is a generalization of this result by Meyer Werner and Werner and Ye for the volume case, for the back measure case, now for the weighted volumes. Okay, and we have in this previous work already observed that when you have these weighted results, you can then use them to derive non-Euclidean results. And we are now doing the same, so this is the reason why we studied this in the first place. We want to introduce some form of LP affine surface area in the non-Euclidean spaces, and we are doing this now with this sort of master theorem, these weighted results. Okay, so to recall here some basic facts. So the classical spaces of constant curvature, hyperbolic space, spherical space, they admit so-called projective models. So what this means is that you can model them over Euclidean space in such a way that the Riemannian metric is chosen in such a way that the geodesics of your space turn out to be affine line segments. So what you can do, and this is very classically, so for the sphere, for instance, you can look at the half sphere and use mnemonic projection to move into a tangent plane. So central projection from the sphere into a tangent plane gives you a projective model. This is usually called the mnemonic projection. You can also do this in hyperbolic space when you identify hyperbolic space with the hyperboloid model in the Lorentz-Minkowski space, so you have an indefinite inner product here. So the takeaway is that this gives you in the end a way to associate Euclidean convex bodies with non-Euclidean convex bodies. And so we will write K bar now for the Euclidean expression of some non-Euclidean convex body. And all we need are hyperplanes and volume measures, and the natural Lebesgue volume measures in hyperbolic and spherical space in these projective models are expressed as weighted volumes with this density function. So in a sense now it becomes very easy. You start with a spherical convex set or hyperbolic convex set. You move into a projective model, you apply these weighted results, weighted curvature measure results, and you obtain some sort of limit theorems in these non-Euclidean spaces. So the only thing that I am missing for now is sort of a polarity operator. Well, there is a natural sort of dual operator on the sphere and also in hyperbolic space. Extrinsically, you can define them in the following way. So you take your spherical convex body, a subset of the sphere. You take the radial extension, this will be a convex cone. You take the polar cone. So you take the intersection of all the half spaces such that the normals of these half spaces are in K. And this gives, when you intersect it again with the sphere, a sort of duality operator. And I chose to reflect in the origin so that the K and K star are in the same half space if possible. Okay, so you can do this duality operator also in hyperbolic space. Here it becomes a bit more intricate because the dual of the hyperbolic space is not hyperbolic space but a Lorentz manifold at the zeta space, a constant curvature Lorentz manifold. But on the level of sets, you can think about the extrinsic model. So if you have a hyperbolic convex set in the hyperbolic model, You can take again the radial extension, you will get some convex cone in the Lorentz-Minkowski space. When you take the polar with respect to the indefinite scalar product of Lorentz-Minkowski space, you will get a convex cone of this form, and you intersect it with the dual to the hyperbolic space, which is the de Sitter space you see in blue here. You will then get some natural so-called de Sitter convex body. So you can define in the same way as in the sphere, also in the negative case for hyperbolic space and de Sitter space, this duality operator that translates in a one-to-one correspondence hyperbolic convex bodies into de Sitter convex bodies. Okay, so now we have all the tools. So our first result for the non-Euclidean case was looking at the volume of the non-Euclidean floating bodies, and it gives you a curvature measure of this form, where you take the Gauss-canonical curvature now again to this magic power 1 over n plus 1. So this is exactly Blaschke's affine surface area now in the non-Euclidean setup, where we take the Gauss-canonical curvature now with respect to the ambient space, so the spherical ambient space, and the surface area measure has to be replaced with the spherical analog to spherical M. Spherical boundary measure with respect to the ambient space of the sphere. And the same is true in hyperbolic space and also the Sitter space. And using, so floating bodies, they are defined as you would define them in Euclidean space. And using our polar theorem and harmonic projections and identifying the projective model with our spherical hyperbolic or de Sitter space, we also can now state the same for these conjugated floating bodies. So when you conjugate your floating body operator with duality and measure the volume and take the volume derivative, they give rise to something that looks like so. So interestingly, the only difference is that the power of the Gauss-canonical curvature changes here. And in a way, these are what we would say the natural analogs to this LP affine surface area we have seen in Euclidean space. Okay, so are they really natural? So this is what now turns out, right? So we started with trying to mimic the same procedure as we have done in Euclidean space in the non-Euclidean spaces, and it gives rise to this curvature measure. And now the question is, are they natural? Are they, in a sense, can we motivate that they really should be seen as sort of LP analogs? Now, it would be very nice to have characterizations in terms of valuation theory, but this is just not accessible. So even for the intrinsic volumes, we don't have really characterization theorems in the non-Euclidean setup. So instead, what we do is we scale the curvature. So we are looking at the sphere hyperbolic space when the curvature is not strictly 1 or minus 1, but lambda. And then when lambda goes to 0, we arrive again in Euclidean space. So if these are the natural notions, then at least when you scale the curvature back to 0, you should arrive at the right notions, the LP affine surface areas or Blaschke's affine surface area in the first case. So this is what we did for the volume of the floating body. So you find when you look at space forms of constant curvature lambda, and you're looking at the volume measure, volume derivative of your lambda floating bodies, they give rise to this expression. And when you scale lambda to 0, you have Blaschke's affine surface area. Okay, so this works nicely and is exactly what we wanted. So this was done previously in joint work with Elisabeth, and now for our polarized notion, we also wanted to have the same picture, right? So when you are starting with these floating body constructions in spaces of constant curvature lambda, and you scale back to 0, you arrive at the classical notions you are used to. So in a sense, a real analytic version of these results is controlled by the curvature of the space. Now, when you do this now with this polarized notion, you have to decide what sort of polarity means for you in these spaces of constant curvature. And the natural thing would be, okay, when you have a sphere of curvature lambda, then the polar should be just a polar sphere where the radius is exchanged by 1 over the radius. Okay, So if you use this identification for the duality operator, then you can take the limit theorem and you obtain in the limit something Euclidean that looks like this. So you obtain a volume derivative of a different object, of the so-called separation, so of the mean width separation body or mean width illumination body, which gives rise to a Euclidean curvature measure of this form. So instead of the p-affine surface area, when you use the usual duality operator, what you find in the limit is a Euclidean curvature measure. So not something that we initially were hoping for. Okay, so the picture looks something like this. So when we have our scaled versions in terms of the curvature, and when we scale the curvature back to 0, we arrive at the separation body, and we have these curvature measures. Now, in the previous case, these two curvature measures were equivalent for the power 1 over n plus 1. And this is not the case for the negative exponent here. So this is a Euclidean notion, so translation, rotation invariant, and this is a central affine notion. So this depends here very much on the point, on this fixed point, the origin, the position of the origin. And here in these notions, they are all translation invariant in a sense, so they don't depend on any fixed point. So our observation was that we have to fix some point in these non-Euclidean spaces and somehow change our polarity operator, and then in doing so we can actually fill this gap here. Okay, so this is the last point I want to make here. So when we change our duality operator, when we scale our curvature of the ambient space, and we have to do this in a, I don't know, maybe artificial way. It seems natural to us, but I cannot guarantee that this will be natural to everybody. So we fix a point E, and we look at convex bodies that contain this point in the interior. And if the curvature of the space is positive, you want that the set is contained in an open half space. Or if the curvature is negative, sorry, the lambda here should be from minus 1 to 0, then you want that the convex body contains a geodesic pole of sufficient radius. Then you can sort of define the duality mapping as a mapping from the space form of curvature lambda again to the space form of curvature lambda. So this was different for just taking the duality operator as usual, by sort of rescaling the cones. Right? So you take the radial extension of your non-Euclidean convex body, you take the polar cone, a dual cone, and then rescale with a linear transformation that just scales in the direction E with respect to the curvature lambda. And in doing so, you obtain a so-called, what we call an E-polarity operator that is now controlled by the curvature lambda. And in particular, when your curvature is plus or minus 1, you just have the usual duality operator, so it does not depend on E. Okay, so conjugating our lambda floating body with this E-polarity, we obtain a limit theorem of this form. And this allows us now, when we go with lambda to 0, exactly this returns the p-affine surface area. So the dependence on E introduced here is exactly what we need to see in the limit again, the p-affine surface area. Okay, so in this way we can complete this picture on the previous slide. So really you have two limiting procedures in the curvature that combine into this one notion in the non-Euclidean space, and we see appearing here two different Euclidean curvature measures, one central affine, one Euclidean rigid motion invariant, that in a very magical way combine into one notion in the non-Euclidean constant curvature spaces. So it seems interesting maybe to study these objects in non-Euclidean spaces and understand more properties of them, to also then derive maybe new properties also for the Euclidean notions. So yeah, very little is known about these quantities. We do know they are valuations, they are semi-continuous in the right way, but yeah, Yeah, we would be very much interested in strong isopatric inequalities. We have some isopatric inequalities for this notion in the spherical setting, but I think many questions here are open and might be interesting to investigate. So thank you very much.